to have Omer Paneth here, this colloquium speaker. Omer did his undergrad in the Open University, his master in Tel Aviv University, PhD studies in Boston University, and now he's at MIT. And I'm going to speak about cryptography outside the black box.
Okay, thanks, Iftach. So hi, everybody. So again, my name is Omer, and I'm going to talk about crypto outside the black box. And please feel free to interrupt me anytime with questions. So I'm going to start with a very brief introduction about my research, what I've been working on. So the traditional paradigm in cryptography, the way we've been doing things since the 1980s basically, is that you have your own machine at home. It contains all of your private data. And now you can use crypto to put this data to use. So you can use encryption to communicate privately over a public channel. And you can also use more advanced protocols like zero-knowledge proofs or secure computation to prove things about your data, to use your data as input to some computation. And you can do all of that without disclosing any additional information to anyone else. What?
Alice and Bob are not talking to each other?
Alice and Bob are talking to you. You are the center. It's very OK, so of course, that's great. But in the last 10, 15 years, our online environment changed a lot, the way we communicate and cooperate with other people online. And this means that cryptography needs to change as well. So today, everyone's private data is online, on the cloud, in social networks, and all kind of online services. This, of course, means that you can do a lot more with your data. But from a cryptographer's point of view, these settings are much more challenging. So first of all, we don't usually have a physical control over our data or over the computations that are running on this data. Also, now we want to consider these applications that are on a much larger scale. So think about applications, these global applications like cryptocurrency or maybe electronic voting, computations that really involve the private data of every single one of us. So a lot of my research is geared towards these modern settings. I've been working on new cryptographic tools that can help us address these challenges. So one area that I did a lot of work on is program obfuscation. So just like you use encryption to protect your sensitive messages, we use program obfuscation to protect our sensitive programs. So using obfuscation, you can take a program that contains your personal information or even your passwords, and you can safely execute this program on the cloud. So the idea is that we kind of jumble around the code of this program such that it remains executable, but now it's so hard to understand that it actually protects your private information. Another area that I worked on is verifiable delegation of computation. So here we're thinking about these really large-scale computation, massive computations that are happening on the cloud. Things like answering database queries or analyzing big data or maybe verifying the consistency of a blockchain. And now we developed this proof system that allows us as users to certify the integrity of these large computations, but the proof itself is very efficient. It's very easy to check the proof. Finally, I worked on a functional encryption. Functional encryption allows you to encrypt your data and put it on the cloud. And it also allows you to get this very fine-grained control over the way someone later can use your data. So you can give someone this token that allows them to evaluate some specific computation over the data and over the encrypted data and learn the results. But other than that, your data remains completely confidential. OK, so in addition to these new cutting-edge tools, I also worked on areas in cryptography that are more foundational. I worked on basic cryptographic protocols like zero-knowledge and secure computation. I'm interested in questions like understanding the round complexity and the secure composition properties of these protocols. Also, I worked on the question of resettable cryptography. We'll talk a little bit more about this question today. And it has to do with running secure protocols on platforms that are not trusted. I worked on different cryptographic primitives. These are kind of the basic building blocks we use to design more complicated systems. For example, cryptographic puzzles are the basic primitive behind applications like blockchains. Fuzzy extractors, they allow us to extract good cryptographic keys out of noisy data. So something like biometric data, for example. And extractable functions are kind of the main ingredient in construction of Snarks. These are these highly efficient zero-knowledge proofs that are currently being used in the anonymous cryptocurrency Zcash. Okay. So in my work, I use a lot of connections between the two sides of these slides. So of course, when we're working on these advanced applications, we always rely on the more classic tools, definitions, and techniques. But this connection also works in the other direction. So we can use these heavy tools that are being developed now to answer more foundational questions in crypto that have been around for a while. And we'll see some examples for this today. Okay. So this is some introduction about my research. What I'm going to talk about in the rest of the talk is one of the main themes in my work, which is how to protect and exploit code. So how can you hide secrets inside programs, and how can you extract secrets from programs? So by looking through this lens, we can see that the results in all these different areas kind of connect to each other. Okay, so let's go ahead and get started. And we'll start with some very basic crypto. So if you ever took a basic crypto course, you probably remember that cryptographers really tend to introduce a lot of notions. So here are some of the basic notions you probably had to learn. So of course, in crypto, we don't just study these notions individually. We study the connections between them. So we have our basic assumptions. These are useful computational problems that we believe are intractable. From these assumptions, we build basic cryptographic primitives. On top of them, we build more complicated primitives. And finally, we have these high-level applications, so cryptographic protocols and schemes that can do all kinds of really amazing things. So now let's kind of zoom in into the most interesting part of this diagram, which is not any one of these individual notions. It's actually the arrows that connect these notions together. So here we have two notions, A and B. These could be assumptions or primitives or applications. So what does it mean that there's an arrow from notion A to notion B? It means that there's a construction that can take any implementation of A and implement notion B. So here it's important that the construction works for every implementation of A. For example, we have a construction of symmetric encryption based on pseudorandom generator. And we have a lot of possible implementations of pseudorandom generators. So no matter which one of these implementations we'll use, this construction will give us a good encryption scheme. Now, of course, we need to say something about security. If we start with a bad pseudorandom generator, we don't expect to get a good encryption. So every one of these notions will also come with its own security definition. And we want that if we start with a secure implementation of A, we get a secure implementation of B. So in other words, what we want is this efficient reduction that can take any successful attack on notion B and translate it into an attack on the original notion A. So really, every one of these arrows translates to a pair of algorithms, a construction, and a security reduction. OK, so now a very important fact. The vast majority of construction and reductions in cryptography are what we call black box. So the implementation of B does not need to know how notion A is implemented. It just needs to use it as a black box, give it some inputs, and learn the corresponding outputs. Similarly, the attack on A will use the attack on B, but it doesn't need to know how this attack is actually implemented. So black box constructions and reductions have a lot of advantages. For example, you can use them even if you don't know the implementation of B or the attack on the implementation of A or the attack of B. Maybe they're given to you by some physical device. Also, as a rule of thumb, black box construction and reductions tend to be much more efficient. OK, so using only black box construction and reductions, yeah. The non-black box constructions and reductions.
Not knowing what's inside the black box can make things less efficient?
For example, if you're using, it's a rule of thumb. It's more like an observation about the techniques that we currently have. It's not a scientific principle. But just as an example, if you're proving something in zero knowledge about a computation of a one-way function, then your dependency on the security parameters of both of these primitives will be kind of multiplied. And we can actually avoid this many times when we design things in a black box way. Of course, I can make something that is black box and it's much less efficient, but this seems to be kind of a good rule. Okay. So using only black box constructions and reductions, we've been able to develop this really rich and beautiful theory, a lot of cryptographic primitives, a lot of connections between them. But of course, this is not the end of the story. It's actually just the beginning. So there's a lot of basic things about this theory that we still don't understand. For example, are there any important arrows missing from this diagram? So can we construct maybe public encryption from any symmetric encryption, or maybe a collision-resistant hashing based on one-way functions? We don't know. Another thing we may want to do is understand the round complexity, the minimal number of messages you need for cryptographic protocols like zero knowledge, secure computation, or verifiable delegation. So all of these questions are currently open, and it turns out that there's some common barrier here. So this is what we call the black box barrier. So what I mean by the black box barrier is that there are many applications where black box constructions and reductions seems insufficient. So we can actually prove that all of these applications and many others as well are just impossible if you restrict yourself to black box reductions or constructions. So I'll just highlight a couple of these applications that I think are in particularly interesting. So basing public key cryptography on one-way functions. This is a foundational question in crypto. It goes back to the seminal paper of Diffie and Hellman. So if you're a theoretician, this question is about collapsing two of Impagliazzo's worlds of average case complexity. If you're a practitioner, this may be an avenue for implementing public key encryption that is orders of magnitude more efficient than one we have today. Another application I want to mention is what we call Snarks. These are these non-interactive proof system that allows us to verify very large computations very efficiently. So these Snarks are currently being implemented in the cryptocurrency Zcash. So there's literally billions of dollars riding on the security of these Snarks. So we have different reasons why we believe that these Snarks are really secure. What we don't have today is a reduction from the security of Snarks to any standard cryptographic assumption. So if tomorrow someone breaks these Snarks, then it doesn't give us an efficient algorithm that can factor integers or solve discrete log or anything like that. Okay, so basing public key cryptography on standard on one-way function, basing Snarks on standard assumptions, these are tasks that may or may not be possible. What we know for sure is that all of these things are impossible if we restrict ourselves to black box reductions and constructions. Okay, so really the main challenge in crossing this black box barrier is the fact that today we only have a handful of techniques that can give us these constructions and reductions that are non-black box. So let me just start by telling you about the techniques that we do have. So in the world of reductions, we have basically one technique coming from the work of Barak. But this technique has been extremely influential. It's been used again and again to cross this barrier. Still, even with the technique of Barak, there are applications that we don't know how to get, and also applications that we do know how to get, but only from very strong assumptions. In the world of constructions, we do have several different techniques that are non-black box. For example, you can take the code of some primitive and prove something about this primitive in zero knowledge, or use it inside some secure computation protocol. But so far, none of these techniques seem to really help us in crossing any of these black box separation results. Okay, so before we move on to talk about some new results, I want to zoom out a little bit and talk a little bit more generally about this question of accessing code versus accessing a black box. So what can you do with the code of some program Q that you couldn't do given just black box access to Q? So this question comes up in a lot of different settings, in a lot of areas of computer science and complexity theory in learning, in mathematical optimization, and of course in crypto. So in all these areas, we encounter these algorithmic tasks where the input is a program, and the type of access you have to this program makes a lot of difference. Okay, so let's start by getting some basic intuition about this question. So I argue that this question is not really interesting in the settings where the program Q is easy to learn. So say that you know that Q is just implementing some linear function. Then if you have black box access to Q, you can completely recover the implementation of Q. So there's really no difference between accessing the implementation or accessing the box. So really what we're interested in is the settings where the program queue is hard to learn. So here's an extremely simple example for a program that's hard to learn. It's what we call a point program or a password program. It outputs 1 on some random password and 0 everywhere else. So this program is hard to learn because it's hard to guess the password. If you cannot guess the password, you cannot learn anything from this box.
You're talking about exact learning also.
Yeah, there's a lot of variance. For this, just the intuition, I'm talking about exact learning. Learning approximation of this function is trivial. Okay. Good. So if I give you this box, you can't learn anything about the password, right? But if I give you the code of this program is so simple that obviously you can extract the password, right? So now the first question that we're going to talk about today is whether you can somehow protect this password. So can you take the code of this program and kind of obfuscate it such that it remains executable, it computes exactly the same function as before, but now it's so complicated, so hard to understand that it actually protects the password just like the black box would have. So protecting programs in this way is called program obfuscation. In the world of security, there is a huge market for obfuscation solutions to protect software against reverse engineering and against hacking. And as we'll see, if you define things correctly, program obfuscation also has a lot of very powerful applications in crypto. The second question that we're going to talk about is kind of the flip side of obfuscation. So can you actually exploit the code of a program, no matter how complicated or obfuscated it is, to learn something about this program that you couldn't have learned by just executing it? So something that you cannot learn from a black box. So really what we're after here is these non-black box technique that can potentially give us the constructions and reductions that cross the black box barrier. Okay, so some of you probably already have the intuition that these two questions are kind of, there's some inherent tension between these two questions. So if we can obfuscate program, if we can create programs such that you can't learn anything useful by just examining their code, this is a major obstacle for designing non-black box techniques. And also in the other direction, if you have non-black box technique, if you have a way to exploit a program's implementation, this puts some inherent limitation on our ability to obfuscate programs. So today we're going to talk about both of these questions. We're going to try and understand where to put the line between how much we can protect and how much we can exploit code. And also we see how we can use the tension between these two questions to develop new techniques, new positive results for protecting and exploiting code. Okay, so our jumping off point for today is Barak's PhD thesis from 2004 on non-black box technique and cryptography. So one of the results in this thesis we already discussed. It gives us the first and only non-black box reduction with applications that cross the black box barrier. There's another work in this thesis that will be very important for us today. It's a work that gives us the first formal definitions for program obfuscation. And it also proved the very important impossibility results. It showed that some programs can never be obfuscated under some very natural definition. Okay, so today we'll talk about some more recent result on protecting and exploiting code. So in the first part of the talk, I'm going to tell you about a new non-black box reduction and its applications. So Barak's technique is no longer alone in the battlefield. So the main ingredient in this new non-black box reduction is exactly the impossibility results I just mentioned for program obfuscation. So here we see an example for how negative results for protecting code actually translate into positive results for exploiting code. So in the second part of the talk, I'll tell you about some developments in protecting code in program obfuscation. So if this impossibility result of Barak et al. Really left us with the sense that obfuscating general programs might be hopeless, then today we think very differently. We had this major breakthrough in program obfuscation about 5 years ago, and today obfuscation is one of the most active areas in cryptography. So I'll tell you about some recent developments in this area. Now, if in the first part we saw a great example for how to use non-black box reductions, in the second part we'll see how to use non-black box constructions to get better program obfuscation. Okay, so let's get started by talking about some positive results on exploiting code with a new non-black box technique. Okay. So the application we have in mind for this new technique is what's called resettable cryptography. So I'll start by telling you a little bit more about this application. So think about some protocol between two parties, A and B. It could be a zero-knowledge proof or any other protocol. So usually we want to guarantee the security of party A, even if party B is cheating, even if it's not following the protocol. But now we're asking for a stronger form of security that holds even against what we call reset attacks. So in a reset attack, party B can reset party A to its initial state. And party A doesn't even know that this reset happened. It just starts executing the protocol again from exactly the same initial state and using exactly the same random coins as it did before. So really, party B can interact with A as many times as it wants, every time it can send completely different messages. So resettable protocols are protocols that are designed to maintain their security even against this type of strong reset attack. So one motivation for studying resettable security is that sometimes we really need to run protocols from platforms that are not trusted, that are really vulnerable to these attacks, platforms like smart cards or virtual machines. Another interesting motivation is to understand the role that resources like randomness or state play in cryptography. So we know that randomness is necessary for zero knowledge, but what we learn from resettable security is that you don't really need to access fresh randomness in every execution of the protocol. You can just access randomness once, and then you can reuse it forever. Even more interesting is that once you have a resettable protocol, you can kind of transform it into a protocol where the parties are stateless. So they don't need to maintain any state for message to message. Okay, so resettable security has been studied in many different settings, different type of protocols, different set of parties that we want to protect. And it turns out that in most of these settings, to get resettable security, we have to use non-black box reductions. And really, all of the protocols we have today are based on the one non-black box technique that we have, the technique of Barak. So today, I'll tell you about this work together with Nir Bitansky, where we give a new non-black box reduction with application to resettable cryptography. And again, the main ingredient in this impossibility results for program obfuscation. So our technique is very different than the technique of Barak. It gives us some concrete advantages. For example, we're able to build protocols based on weaker assumptions with less rounds. Also, all of our protocols kind of follow the same simple design. And this is in contrast to previous protocols in this area that were kind of ad hoc, and many of them were extremely complicated. Also, all of the protocols based on Barak techniques are heavily relying on the PCP theorem. Our protocol does not use any PCP techniques. So I don't see this as an advantage. It's just to demonstrate the differences between the two techniques. Yeah.
Can you please explain the basic rules of obfuscation? I mean, who knows what? Who can run the program? Who obfuscates the program?
So I'm going to explain. There's a slide in a couple of minutes. Before we're going to use obfuscation, we'll see the slides. But just in general, an obfuscator is a compiler that takes input a regular program written in like however you can understand the code. That's the human written language. And the obfuscator translates it into a different program that is still perfectly executable. You can run it on your computer, but if you examine its code, and it could be machine code or high-level code, then you can't learn anything about what this program does, how it does it, that you can't learn by just executing this program.
But I have the executor myself.
You have the program. What you don't have is the compiler. You don't. Maybe you know how the compiler works, but you don't have the randomness that it used in order to produce this program. So something like encryption. You have the ciphertext. You don't have the key. Okay. Okay. So I'm going to tell you about this new technique, and I'm going to explain it through an example application, how to identify yourself using a smart card. So let's start with a joke. So you walk into a bank, and you want to identify yourself. Before you can do anything, you need to identify. You have your own secret key. It's known only to you. And the bank has some corresponding public key that it uses in order to check your identity. And now you use these keys to run some identification protocol. So now we want to make the identification process as easy as possible. So we give the clients these smart cards. And the smart card contains the secret key, and it can actually run this identification protocol for you using the secret key. So of course the smart card is shielded. If my smart card falls into the wrong hands, nobody can kind of pry it open and see the secret key. But the smart card does not have its own power supply. It doesn't have its own source of randomness. So it's really vulnerable to these reset attacks. Okay, so the security requirement we want from this protocol have two parts. First of all, we wanted the smart card protects the secret key. So if someone gets temporary access to my smart card, they can't interact with this card and extract my key. The second property that we want is that you really have to know the right secret key in order to identify, so nobody can claim your identity. So say that there is some program that correctly identifies against your public key, then this program has to know your secret key. What does it mean that the program knows the secret key? We mean that there is an efficient redaction that takes the code of this program and extracts from it the secret key. Okay, so now I argue that in this type of application, we cannot get the reduction in the second part of the property to be black box. It has to exploit the code of this program. And intuitively, the reason is that if we had a reduction that is black box, we would kind of get a contradiction between these two properties. So if the reduction can extract the secret key by only accessing this program as a black box, this means that the adversary can just use the same strategy as the reduction and extract the secret key out of the smart card. So really, the challenge in designing such a protocol is that you must design a reduction that somehow exploits the code of the program to extract the secret key. But this sounds like a very difficult task because we have no idea how this program is implemented. It can be as obfuscated as it can be. So here we're really going to exploit the fact that some programs just cannot be obfuscated. Okay, so let's switch gears for a little bit and talk for a minute about obfuscation and the impossibility result. So Barak and I will show an impossibility result for a very natural notion of obfuscation called virtual black box obfuscation. So a virtual black box obfuscator is, again, a compiler that takes as input programs and outputs obfuscated programs. So the obfuscated programs is executable, and it has the same exact functionality as the original program. But in terms of security, this obfuscated program is like a virtual black box. So what I mean by that is that anything you can learn by looking at this obfuscated program, you could have just as well learned given a black box that computes this program. And this is not a formal definition, but it does give us the right intuition here. Okay, so to prove that virtual black box obfuscation is impossible, Barak et al. Demonstrate a function f that cannot be obfuscated. So this function is parameterized by some secret key k, and this key is hard to learn. So if you have black box access to this function with a random secret key, you can't learn the key. But at the same time, this function is designed in such a way that you can actually learn the secret key from any implementation of the function, no matter how obfuscated or complicated this implementation is. So such a function can really clearly not be obfuscated because from any obfuscated implementation of this any obfuscated program that implements this function inherently leaks the secret key. So the most remarkable thing about this result is that extracting the key from the obfuscated program is done in a non-black box way. So I'm not going to go into details, but the high-level idea is to use some sort of diagonalization. So if you take this obfuscated program and you execute it on its own code, only then you can somehow learn the secret key k. Okay, so in our identification protocol, we're not going to use this impossibility result as is. First, we need to strengthen it a little bit. So in this work, we give a stronger version of this result. We show that some functions cannot be obfuscated, even approximately. So even if we allow the obfuscated program to make some mistakes and compute the function incorrectly on most of the inputs. So really, everything stays the same, except now we want that it's easy to learn the secret key from any approximate implementation of the function. So an approximate implementation is something that computes the function correctly on some small polynomial fraction of the domain. But everywhere else, it can refuse to compute the function, output some symbol bottom. So by the way, under some stronger computational assumptions, we can even extend this result to support arbitrary errors from the obfuscated program, not just erasures. But we're not going to need this today.
given the extractor key, you can verify that it's a correct key, at least?
Yeah, I mean, in this definition, you don't have to do it, but if you could make arbitrary errors, you definitely need some sort of verification, or maybe you can output a list of possible keys, something like that. Okay, so if you look at the original impossibility of Barak et al., there, if the obfuscated program computes the function incorrectly, even on a single point, then we may already completely fail to extract the key. So what we do here is give a more robust version of this function f that has some random self-reducibility properties. Okay, so back to constructing our smart card identification protocol. And again, the main ingredient that we're going to use is this function f that cannot be approximately obfuscated. So the protocol looks like this. The secret identification key is just the secret key k for the function f. And the public key is some encryption of this key. So now in the protocol, the bank just sends you a random input, a random challenge for this function. And the smart card needs to evaluate the function on this input and compute the output y. And the smart card will also give you some proof that x and y are consistent, that y is equal to fk of x, and k is really the right key that is sitting inside the public key. So just for simplicity, you can think about this proof as being a zero-knowledge proof. It gives you no additional information about the key k. So actually, implementing a zero-knowledge proof that can run on a smart card is pretty challenging. So I'm not going to go into much details, but we can actually do is change the protocol a little bit and use something simpler called a witness indistinguishable proof. Okay, so the intuition here is that we designed our protocol so that in order to identify yourself, you need to evaluate a function that cannot be obfuscated. This means that in the security reduction, we can always somehow exploit your code to extract your key. Okay. So let's see how this works. So to show that the smart card really protects the secret key, because this proof is zero knowledge, then all the adversary gets by interacting with the smart card is just black box access to some box that computes the function fk. And we know that from this type of access, you cannot learn the key. So now to argue that you have to know the secret key in order to identify, say that there is some program that identifies correctly. So because the program is proving that x and y are consistent, then the program has to compute the function correctly, at least on some of the inputs. So there could always be some inputs where this program refuses to identify. And in this case, we say that the program outputs bottom. So we get this program that approximately computes the function f. And since the function f cannot be approximately obfuscated, we know that there is some efficient way to extract the secret key out of the code of this program. Okay, so this was just one example application, but we use this idea of embedding some function that cannot be obfuscated into the protocol. We use it in many different settings, and we get different type of new resettable protocols in all kinds of settings. Okay, so we talked a little bit about positive results for exploiting code. So let's move on to talk about how to protect code, how to obfuscate programs. And again, we'll see a great example for the power of non-black box constructions here. Okay, so let me start with some of the important milestones that led us to this major breakthrough in program obfuscation. So we already talked about this result in 2001. Barak et al. Gave an impossibility results for virtual black box obfuscation. So this could have really been the end of the story for obfuscation. But actually, the same work also kind of planted the seeds for the positive results that are going to come ahead. So this work also defined a weaker notion of obfuscation called indistinguishability obfuscation, or I/O for short. So at the time that it was defined, it wasn't at all clear that I/O is even useful for something. But what was clear is that the notion of indistinguishability obfuscation is so weak that it actually escapes the impossibility result that we have for virtual black box obfuscation. Okay, a year later, in 2002, Bonnet and Silverberg suggested a new notion that they called cryptographic multilinear maps. And they showed that these maps, if they exist, would have far-reaching consequences in cryptography. Fast forward to 2013, Garg, Gentry, and Halevi gave a plausible construction that gives us a good implementation of these multilinear maps based on ideal lattices. And very shortly after, based on these multilinear maps, Garg et al. Gave the first candidate construction of indistinguishability obfuscation for all programs. So this chain of events kind of put the notion of indistinguishability obfuscation front and center. And very quickly, indistinguishability obfuscation became a very popular notion. So I think that one of the reasons that I/O became so popular so fast is that it really strikes this, the right balance between usability and achievability. So it's not too weak, it's not too strong, it's kind of just right. So in terms of achievability, we already mentioned that I/O is not subject to the same impossibility result as virtual black box. And also we have these candidate constructions now that we don't know how to attack based on multilinear maps. And in terms of usability, in the last 5 years, we've been discovering more and more applications of I/O all over cryptography. And even outside cryptography, we can show that indistinguishability obfuscation can help us to prove the hardness of computing a Nash equilibrium in a game. This is an important question in complexity and algorithmic game theory. So the definition of obfuscation, of indistinguishability obfuscation, is very simple. It says that if I give you two programs of roughly the same size that compute exactly the same function, so these are just two different implementations of the same functionality, then if you look at the obfuscated versions of these programs, then these obfuscations will be indistinguishable from each other, so they cannot be distinguished by an efficient observer. Okay, so we're not going to use this definition too much in the rest of the talk, but I just want to give you some intuition about it. Specifically, I want to demonstrate the differences between indistinguishability obfuscation and virtual black box. So here we have, for example, two programs. One of them is a password program that outputs 1 on a random password, and the other just always outputs 0. So now we look at the obfuscated versions of this program and we ask whether they're indistinguishable from each other. So if we use virtual black box obfuscation, then I argue that the answer is yes, these programs are indistinguishable, because if we look at them as black boxes, the only way to distinguish them is to guess the password. But what if we're only using a distinguishability obfuscation? So here these programs are not functionally equivalent. They behave differently on the password. And this means that the security guarantee of I/O does not guarantee indistinguishability in this case. But it turns out that if one-way functions exist, we can show that these two obfuscations are really indistinguishable. It requires a non-trivial proof. So the bottom line here is that this notion of I/O really seems much weaker than virtual black box obfuscation. This is also why we can escape the impossibility results. But it still turns out to be very useful, at least once you figure out exactly how to use it. Okay, so if the notion of I/O is so useful, then today one of the most important research directions in this field is to base the security of I/O on solid foundations. So let me explain what I mean by that. So we started with this construction of obfuscation based on multilinear maps. Originally, this construction did not have any proof of security. So now the next big step towards understanding the security of I/O was to give some reduction from the security of I/O to the security of multilinear maps. So today, if you can attack the I/O construction, you can also attack our multilinear maps. The only problem is that we already know how to attack our multilinear maps. So in the last few years, there's been several powerful attacks on our multilinear map constructions. Now currently, these attacks don't translate to full-fledged attack on our obfuscation construction. We can kind of tweak our constructions to resist these attacks. But still in this case, our obfuscation construction can still be secure, but our reduction doesn't give us any additional confidence that this is really the case. So really today we've been working on understanding the security of I/O in two different directions. One of them is to build stronger multilinear maps. And the other direction is to base obfuscation on something weaker and prove the security of obfuscation based on more standard assumptions. So we already did a lot of progress in these directions. Before I tell you about this progress, I just want to take a minute and talk a little bit more detailed about this notion of multilinear maps. So multilinear maps are this generalization of notions like cyclic groups and bilinear maps that we've been using in cryptography for a long, long time. So we have this degree parameter k. K equals 1 corresponds to a regular cyclic group. K equals 2 corresponds to a group with a bilinear map on it. And we can also define a group with the k-linear maps for larger values of k. So in a regular cyclic group like ZP, like the multiplicative group of ZP for some large prime, we can always take two elements, g to the a and g to the b, and multiply them to compute g to the a plus b. But we believe that multiplying in the exponent is hard. So we believe that it's hard to compute g to the a times b. This is the computational Diffie-Hellman assumption. So intuitively, you can only evaluate linear functions in the exponent. So in a group with the bilinear maps, for example, these pairing-friendly elliptic curves, you can do one multiplication in the exponent, but the result is under some different representation of this group, so you can't apply this operation again. In fact, we conjecture that it's hard to multiply even free elements in the exponent. So more generally, in a group with a k-linear map, you can always evaluate polynomials of degree up to k in the exponent, but evaluating polynomials of higher degree should be hard. So Gargedal suggested an approximate construction for such a k-linear map. So every group element the representation of every group element is in some sense noisy. And also we know that there are some attacks on this construction. So not everything that is supposed to be hard really is hard. Still, we can do a lot with these multilinear maps. So in recent years, more candidates have been suggested, even more attacks have been suggested. So I think it's fair to say that today we don't really understand the security of these multilinear maps. Okay, so in terms of applications, these groups have applications all over crypto. And of course, the higher the degree is, the stronger the applications. And if you use multilinear maps of high enough degree, you can actually get a full-fledged program obfuscation. So to summarize these tables, we have this kind of hierarchy of objects. The higher degree is, the stronger the applications, but also security becomes more tricky. So now a very natural and important question is whether we can reduce the degree of the multilinear map we need in order to get obfuscation. And of course, the ultimate goal here would be to reach degree 1 or 2, where we really have a better understanding of these objects and their security. Okay, so how low can we go? What is the degree of the multilinear maps that we actually need to get obfuscation? Yeah.
But, I mean, you argue that you can't actually get obfuscation, full-fledged obfuscation, right?
So I'm talking about indistinguishability obfuscation.
Oh, so that's IO.
Yeah, sorry. Yeah, I think for the rest of the talk, I'll mainly focus on I/O, but I'll mention if I'm not. Okay. So what is the degree of the multilinear maps that we need to build obfuscation? So the original constructions used a degree of the multilinear map, which is some high polynomial. So of course, we want to push it down, but here we encountered our old friend, the black box barrier again. So it turns out that you cannot base obfuscation on any constant degree multilinear maps with a black box construction. So if you had, what I mean by that is that if you had such a black box construction, you can kind of transform it into a new construction that doesn't even use the multilinear maps. So intuitively, in the black box world, constant degree multilinear maps are kind of useless for obfuscation. Okay, so don't let this negative result discourage you. The right way to interpret this result is that it kind of points us in the right direction. And this direction is non-black box constructions. So shortly after this negative result, in a beautiful sequence of work that eventually gave us a construction of indistinguishability obfuscation from degree 3 multilinear maps, together with a new assumption on local pseudorandom generators. So of course, this construction is non-black box. It exploits the code, the implementation of these multilinear maps. So really now we're on the verge of basing obfuscation on standard assumptions. We're not there yet, and any improvements for this picture from now on will be extremely exciting. So today I'm going to start by telling you a little bit more about this negative results, and then I'll try to give you the intuition of how we can exploit the implementation of the multilinear maps to do better. Okay, so here we have some obfuscator that uses multilinear maps in a black box way. So what I mean by that is that the obfuscator, we can look at it as having some access to a black box that implements the group operation and the multilinear map, So the obfuscator itself doesn't care how group elements are actually represented. It just manipulates them using this oracle. Of course, the obfuscated program that we produce also needs to access this oracle in order to manipulate the group elements. So now what we show in this work is that you can also always take this obfuscator and translate it into a new obfuscator that does not use the oracle at all. But this new obfuscator is only approximately correct. So it produces programs that give us the right answer on, say, 90% of the inputs. So we do pay some price here in correctness. I argue that this is not a real price. So in the settings of virtual black box obfuscation, we already seen that approximate obfuscation is just as impossible as exact virtual black box obfuscation. In the setting of indistinguishability obfuscation, we can actually fix this obfuscator. We can translate it into an obfuscator that is perfectly correct, assuming only one-way functions. Okay, so this is what we want. This result was proven in 2 steps. In the first step, in the work with Canetti and Kalai, we showed this, where the multilinear map is replaced with a random oracle. So a random oracle is just a black box that computes a random function. Every new query that you give it, it gives you an independent random value. So this random oracle doesn't have any group structure. So then Pass and Chalet show how to extend these techniques to support also a constant degree multilinear map. So today I'll tell you about the first part of this theorem, how to get rid of a random oracle. So the proof is not complicated, it's just one slide. So we start with some original obfuscator that uses a random oracle. And now we want to build from it a new obfuscator that takes as input a program Q. And it just emulates the original obfuscator. Now the original obfuscator needs to access the oracle, so the new obfuscator will kind of emulate this oracle for it. So every time the obfuscator makes a query, we answer it randomly and independently. And we denote the set of all the queries and answers that are performed in the stage by R. So now the original obfuscator is done making queries. It spits out an obfuscated program P. And remember, this program P also needs to access the random oracle. So we need to answer the queries made by this program, and we better answer them consistently with the set R, because if we answer them differently, we may completely lose correctness. So one thing we can do is just emulate this program together with the set R. So we include the set of queries and answers together with this obfuscated program. And every time, if the program makes the query QI, we answer by AI. And if the program makes a query outside the set R, we just answer this query randomly. So really, whatever we answer the queries that are outside the set R, it doesn't make a difference. The original obfuscator never made these queries, so the answer could not possibly affect the correctness of this program. Okay, so this is one thing we can do. Of course, there's a big problem with this suggestion. What is the problem?
Need to obfuscate R.
Yeah, so if you just give R in the clear, you completely lose security, right? R can depend in an arbitrary way on the set on the original program Q. The original obfuscator can actually make a query that actually encodes the description of Q. So instead, what we're going to do is use a different set H. Then intuitively, this H is kind of summarizing the important part, the part of the random oracles that are important for the set P, for the program P. So we want to design this set H in such a way that it will not affect security, but at the same time, it will give us at least approximate correctness. So we define H to be the set of heavy queries that the program P makes. So the set of queries that P makes with probability more than some threshold epsilon when you execute it with a random input and with this random oracle. So really, the new obfuscator is going to get this new program P, and before it outputs it, it's going to approximate the set H. So we can efficiently approximate the set of heavy queries. And also, if this threshold epsilon is not too small, then the set of heavy queries will not be too big. We can actually hard-code it into the obfuscation. So now I need to argue that the set H is good. It gives us security and at least approximate correctness. So the reason that the set gives us security is that the way we defined H, it only depends on the code of the obfuscated program P and on this random oracle. But by the security of the original obfuscator, anything you can learn from the obfuscated program is kind of public. It cannot compromise security. So for example, this obfuscated program will never make a query that depends on the code of Q. So to show that the set gives us approximate correctness, I argue that the only way that this program can make a mistake is if it makes a query to age that is, if it makes a query that is in the set R, but is not in the set H. So if you make a query that is outside the set R, we already said that the answer to this query cannot affect the correctness. If you make a query that is inside the set H, then you have consistency between the answers of the random oracle and the answers in H. So really the only bad case is if you query something in R that is not heavy, that is not in the set H. But if we set the threshold epsilon correctly, then we can really bound the probability that we ever see a query that is not heavy. And we can say bound it by maybe 10%. And this is how we prove approximate correctness.
But if we just query a random input,
Mm-hmm.
with probability 1, I'm querying something which is not heavy.
Okay, but it won't be in the set R, because the set R is small. It can contain a random input with a good probability.
So how is R defined?
So R defined as all the queries and answers that the original obfuscator makes in the process of creating the obfuscated program. So we emulate the original obfuscator, we simulate the oracle for it, and it makes some small set of queries. And we only care about answering consistently inside the set, right? So if the program P makes
R is a random variable.
R is a random variable, right?
So what is heavy here? So I'm slightly confused about the definitions and what's random variables.
Okay, so in the construction, we output a set age that really depends only on the program P that we got. But we got it from the specific experiment where we emulate the queries and answers. So this program P has some specific set R that is.
I see. Okay, you fixed one experiment.
Yeah. So now in the analysis, so of course, when I define age, I define it only based on the obfuscated program. It cannot depend on the set R, otherwise I lose security. But in the analysis, I argue that the only queries that are actually important are queries that fall in the set R. So if this program makes a random query, for example, that's fine. I won't know how to answer consistently, but it doesn't matter because this query was never made, was never queried by the original obfuscator. So it can't affect security. It can't affect correctness. Okay. Okay, so this was the proof.
You still have to argue why releasing H is fair now, even if after you do that?
Why is it secure?
Yes.
So intuitively, it's secure because age can be simulated only given the code of P. And therefore, the security follows from the security of the original obfuscator. That make sense? Okay. So I'll tell you about this negative result. I'll just mention that following these results, these techniques were significantly generalized, and they were used to give us a very good picture of the type of objects we can use to build indistinguishability obfuscation from. So now I just want to say a few words about the non-black box construction. So these non-black box construction of obfuscation have this really cool structure, this recursive structure. So when I evaluate the obfuscated program P, it will internally run the code of the obfuscator and produce a smaller obfuscated program that will output a smaller program and so on until eventually one of these programs actually give me the output. So these constructions are non-black box. We're using the code of the obfuscator and also the code of the multilinear maps inside our obfuscated program. So intuitively, in this negative result, we crucially use the fact that the obfuscator will only make a small number of queries to some black box, so we can somehow summarize all the important queries that the obfuscator makes. But in these constructions, we run the obfuscator as part of the evaluation process. The programs that we're obfuscating here can depend on the input X. So there's really no way to predict ahead of time what are the important queries that all these obfuscators are going to make. So this is how these recursive constructions get around the impossibility result. Okay, so let me summarize by talking about some future research directions in this area of protecting and exploiting code. So we already talked about a lot of open questions related to program obfuscation. One question that I find interesting is to explore the space between the positive results we have for I/O and the negative results for virtual black box obfuscation. So can we maybe identify meaningful classes of programs that we can get positive results for a virtual black box obfuscation? Maybe we can also identify interesting notions of obfuscation that lie between IO and VBB, where we can maybe get general positive results. So moving on to the direction of exploiting codes. So today we have two non-black box techniques, not one, we have two. Both of these techniques are based in some way or another on this idea of diagonalization. So what else we can do? What else can we do? And there's really a lot of applications that we can tackle here. So let me just mention two applications that we already made a lot of progress on, but we definitely need some new techniques to completely resolve these questions. So one application we already mentioned, basing Snarks on standard assumptions. So Snark allow us to prove the, for example, we can use them in the context of blockchains to prove the consistency of the transactions on our blockchains, but we can use the zero knowledge property to protect the anonymity of these transactions. This application of concurrent security, can we design protocols that where many copies of the protocols can run concurrently at the same time on the net without losing security? So both of these applications can help us design these large distributed systems that maintain security and can maybe be scaled to a real world scale. So the next question I mentioned is kind of the flip side of this. So can we actually go beyond black box lower bounds and prove the limitations of arbitrary, even non-black box reductions? So we already made some progress in these directions. We proved limitations on constructions of very strong primitives. And perhaps not surprisingly, one of the main tools we use in these lower bounds is the existence of indistinguishability obfuscation. So here we again see an example for how positive results on protecting code give us the limitations on exploiting codes. That's it. Thank you.